Okay, so we're going to be doing this question right here. If you're wondering where this is from the 2018 AP Physics 1 exam free response. This is question 1, so the very first one, so you can actually look it up and do it for yourself if you want to. But here I'm just going to walk through it. So just talk about the thought process, because I guess something like this problem has a lot to do with something called a derivation. And it's kind of interesting to start thinking about derivations and using formulas that we know and combining them together. And then we're also going to be doing a lot of reasoning mathematically. So like learning what happens when you increase a variable, how do you know what to do with those types of problems. So here it is. A mass of a spacecraft of mass m is in a clockwise circular orbit of radius r around Earth as shown in the figure above. The mass of the Earth is that, m sub e. In the figure below, draw and label the forces that act on the spacecraft, and then the second sentence talks about how you should draw it. So maybe this one already screams out to you what the answer is, but if not, if you remember from when we studied circular motion, if I have a circle, we have a particle right here. Let's say it is a spacecraft, and then the center is the Earth. There's actually, it has to be moving, and its velocity is given by a tangent vector at that point. But then, if we were to only talk about the velocity, then it's only going to be traveling this way. It's not going to travel in a circular motion. So there must be something supplying that change in direction for velocity that makes it go around the circle. And that is something called centripetal acceleration. Centripetal acceleration makes the particle start traveling in circles, and it always points directly at the center. And then using Newton's second law, we know that if there is an acceleration pointing somewhere, there should be a force, right? There should be a force acting on that object. So that means this acceleration can be thought of as the force, because it has to be pointing in the same direction as well. So in this diagram, we actually have a force vector. That's not a great arrow. Let me use the arrow tool. A force vector pointing at the Earth. Pointing at the Earth. And what type of force is this, right? I guess the first mistake many people will say is the centripetal force. So they'll say F sub c and then they'll go to the next one. But this is wrong. There's not really a thing called centripetal force that you label on the diagram. Something must act as the centripetal force. So there's no such thing as a centripetal force because something has to act as the centripetal force. So what is that force acting as the centripetal force? Well, since it's talking about the Earth and a mass, a lot of mass, right, is in Earth. When we associate Earth, we kind of think of gravity. It is the gravitational force, or the force due to gravity. Okay, so this is the part A, so let's move on to part B. This is where we'll start deriving equations, and derive an equation for the orbital period t of the spacecraft in terms of m, the mass of the Earth, the radius, and the physical constants as appropriate. If you need to draw anything, draw it, use a space. So you can't draw it here because this is what they're going to be grading. And let's just do A. So A, I'm going to scroll to the right and start working it on the right here. Something is just happening. Okay. So, in thinking about this, orbital period, that's a good thing where the place to start, right? Orbital period, so we're talking about the period. Is there an equation we know for period? Well, what does period mean, right? That's the first thing. Period means if you go around in a circle or something that repeats itself like a circle. A period is exactly the amount of time it takes to travel that one orbit or one revolution or one rotation. It's that time that it takes to travel one rotation. So we'll be thinking about that. So the way I'm actually going to write an expression for period is know that the velocity is equal to distance over time. And if I say the distance is the distance of the circle, that means if you do one rotation of the circle, it must travel the period, or t, capital T. So it's In other words, it's distance over time, like this. Speed is equal to distance over time. But what is that distance, right? We can't just say distance, because that doesn't give you a lot of information. You have to say how much does it travel. It travels the circumference of the circle, 2 pi r. 2 pi capital R, because that's the variable we're working with. This is an expression or an equation we can use to find the period. And I'll just keep it like this because maybe we'll see why I'll show you why we need it later. You can actually, if you really wanted to solve for the period, but you'll see that you shouldn't, because it will actually be more work. Okay, so now what? How do we relate the period, which we found an equation for, with the spacecraft and the mass of the Earth and the radius? Right, we have the radius, we need the mass of the Earth. That's kind of weird. Well, let's look at part A again. Part A. We found the force due to gravity. Let me write that here. The force due to gravity. What is that? Is that an equation? It is mg, but we want to talk about it in terms of the mass of the Earth. This mass is the mass of the spacecraft. We want to use the law of universal gravitation, where this is the mass of the spacecraft and this is the mass of the Earth, and then this is the distance between them. But it is also supplying a circular motion, so the force is equal to mass times centripetal acceleration from Newton's second law. So what I did here was this, and then this goes to here, and which is equal to that, and then it's equal to this. So in all, G is G times the mass of the spacecraft times the Earth, like this, is equal to mv squared over r. So we do have all the variables we need. We have two kind of equations that are kind of linked, so let's actually combine them, right? I know what v equals. I can substitute that in. So let me do it over here. G little m. I guess actually first, I noticed that this mass cancels out with this mass, meaning that this equation does not depend on the mass of the spacecraft. That's actually an important note. Sometimes in equations you cancel stuff out. That means it is not dependent on it anymore, right? If you plug in 2m, or twice the mass, since it's equal to twice the mass, you can just get rid of it. So G, as the mass of the Earth, divided by r squared, is equal to v squared. So I'm going to do it like this. V squared, which is 2 pi r over t squared, right? I guess I can get rid of one r pretty easily. So then we're left with what? What are we left with? We are left with G times the mass of the Earth divided by r is equal to 4 pi squared. That's kind of weird. We see a pi squared. R squared divided by t squared. And then I guess since our goal is to ultimately find the orbital period t, so we should probably solve for t, and that's pretty easy. So t squared is equal to what? 4 pi cubed r cubed, or not pi cubed, it's pi squared. It's still the same pi, but what I did here was multiply both sides by r to get rid of that denominator, and then I'm just going to divide by gm. Yeah, and this is just algebra. So I'm going pretty quick on the algebra, but if you really want, you can slow down here and just, I guess you can cross multiply. That's probably what I would do. So we have t equals that, but in other words, that means t equals the square root of that. And there we have an equation, or we derived an equation for orbital period in terms of the masses, the radius, and any physical constant, which is g, capital G, or big G. So now we move on to the second part. Copied what we found right here to answer the second part. A second spacecraft of mass 2m is placed in a circular orbit with the same radius r. Is the orbital period of the second greater than, less than, equal to the orbital period of the first one? So that's kind of interesting. So it's what this question is asking: does the mass of the spacecraft actually matter in determining orbital speed? Looking at this equation, we notice that there is no mass of the spacecraft in this equation, meaning that it does not depend on it. In other words, if we were to pretend the mass was 2m and we plug it into this equation, everything else is the same as it was in the first case. So it is equal to. And the reason why is because we canceled it out in this step right here, and we saw that masses appear on both sides, and we can get rid of them, so it's not dependent. So when it says briefly explain your reasoning, you can say the equation for orbital period, I guess you can say, does not depend on the mass of the spacecraft. It's briefly, so you can even just say a one-sentence statement and you'll be fine. Moving on to the part C. The first spacecraft is moved to a new circular orbit that has a radius greater than r, as shown in the figure below, right? Is the speed of the spacecraft in the new orbit greater than, less than, or equal to the original speed? So we need to relate all these ideas, right? The mass of the Earth, the radius, into this thing. So we use what we just did right here, mv squared over r, and then in other words it's m like this, right? I'm just copying what we did in the previous example, just rewriting it. I guess now we solve for the speed because we are not determining period anymore. So speed, so let me just multiply by r. So v squared is equal to gme over r. And I guess if you really wanted to, speed is equal to the square root of gme over r. So because we want to compare the speeds when you do this. Is the speed of the spacecraft in the new orbit greater than, less than, or equal to the original speed? We increase the radius, so what happens in this equation, right? We want to compare. What happens if I do this? What happens if I replace this with, let's just say, the new radius is 4 times its thing. You can choose a huge number if you really wanted to make sense, right? If you choose 1000, it makes a lot of sense, but I'm going to choose 4 for a very specific reason. It's just that I can take out a square root of 4 is 2, so it's just v, or this, so this is case 1 and this is case 2. So case 2 is equal to 1 over 2 square root of gme divided by r, right? This is the same, I just took out that 4. But notice that this is the same as this. In other words, I can replace it. The new speed is equal to half of whatever the original one, meaning that it is less than. And I just chose this number 4 just conveniently, just to show you that this is how you actually do stuff with problems like 2 if you had a mass appear. You want to substitute that in, try to get a form of the original case, and then you can substitute the original case here and then see how they're related to. So in this case, the second case has a half speed of 1, meaning that is less than. But for this question, you can just say, as you increase the radius, since it's in the denominator of the fraction for determining speed, as you increase the radius, the fraction gets smaller, meaning that the size of the speed gets smaller as a result. So you can just say that, and that's good enough. So that's it with this problem. As you can see, it's just getting used to deriving an equation and using the equations to help us with explaining stuff when we change something. So that's it for this video.